And all right, so let me actually go back a second. All right, so welcome everybody to the Intro to Spatial Analysis in R workshop for Mark, or for the JCOIN network. This is one of many Mark workshop series that our group is hosting. Today we're going to be talking about geocoding and linking community data, and this is a fully interactive live workshop. So the first 15 minutes I'll be going through some basics of who we are, why we're doing what we're doing, and what the plans are for today. But then the rest of the workshop is really going to be dedicated to actually hands-on keyboard, getting some code out, hopefully making some mistakes, and then debugging those mistakes to kind of get to the next stage. So I'll tell you a little bit about the three of us who are co-hosting the workshop series together. Each of us will be leading different workshops. So myself, I'm Marynia Kolak. I lead up the Healthy Regions and Policies Lab at the Center for Spatial Data Science at the University of Chicago. I am a health geographer, but also a spatial epidemiologist and spatial data scientist. I'm really interested in how where you live is associated with your health outcomes and what those different types of interactions, drivers, impacts are. How can we measure them, as well as how can we distill those different factors. Jimmy, did you want to introduce yourself quickly?
Hi, I'm Timmy. I'm postdoc at the center. I have a background in quantitative methods, causal inference, but also right now I try to learn more and work more in spatial analysis. Think about how context is, how spillover, how your connection with people, and also your connection with your exposure to your neighborhood affects your health outcomes, etc.
And Susan?
Hi, everyone. I'm Susan Pakin. I'm the research project manager for the Healthy Regions and Policies Lab. I come from a background in policy research and analysis, and also in spatial data science and analysis as well. So merging those two fields together and applying the research that we're producing out of the lab, particularly around opioid risk environments, and translating that to a broader audience.
And so again, this is our team. And what we'll be talking about today for our workshop, first, I'll give you a little bit of an introduction, even more so than I already have, but we'll talk a little bit about what is what the workshop series is all about, what are the topics that were already covered, as well as what are we going to be doing next. Then I'll provide a bit of a spatial data overview for those of you who've already been to the first part of the workshop. Some of that will be a review. However, we do offer some slightly new updated pieces to kind of further deepen your understanding of what spatial data is. Next, I'll briefly talk about setting up your R environment, but I am assuming that if you're attending, that you have a basic knowledge of R already. What do I mean by that? You will have R in RStudio installed on your system, and you know how to set up a working directory. I'll also give a few tips about that, but hopefully that basic component is there. And then you also know how to install some libraries. So while, so myself, I'm leading it this time, and then Xiuming and Susan will support in assisting one-on-one questions as needed. It will be a bit more fast-paced than one-on-one completely. So that being said, this workshop is being recorded, and all the code that we're going to be using is also freely available in a pre-packaged toolkit. So even if you can't get through everything or one part of our workshop today, you'll have plenty of opportunity and resources available to you after to again resolve at a later time. That being said, we will be having some live demos and live coding. We're going to geocode some resources, conduct a very basic buffer analysis, and then start linking community data. Based on user interest, we may also, we'll kind of go through some of the basics of accessing census data on your own through the API. I won't go through in detail the same type of live coding that I will for the other pieces here, but for those of you who are up for that challenge, we also have resources available to link up with that. So first, let's do some introductions. You know a little bit about us. We'd love to learn more about you. So in the chat, please share your name, your affiliation, and interests that led you to this workshop. Again, we ask everyone to do that, and we already did our part. So hopefully you will do the same. As you're doing that, I'll just talk a little bit about the workshop series. This workshop series is entitled The Spatial Dimensions of Opioid Risk Environments. This is part of the Methods and Analytics Center that is based at UChicago. And this Methods and Analytics Center is part of the wider JCOIN network. So JCOIN stands for a Justice Community Opioid Innovation Network. All of you are here because you're in some way affiliated with that JCOIN network. So again, our Method Center, we are here to not only do research on spatial extensions of the opioid epidemic, and as you can tell by the title, our job is to really contextualize, quantify, and better understand the opioid risk environment perspective, like from a community place-based perspective, that can then inform individual level or population level health outcomes. But we don't only research that. Our job at the Method Center is to really make that type of analysis and insights and visualizations accessible to other groups. So we're here also in a way to consult, guide, provide workshops for understanding spatial analysis in opioid risk environments. So the last workshop Susan led talking about what spatial analysis for opioid risk environments is all about from a very macro perspective. A big feature of what we've already generated is a massive spatially enabled database that of dozens of different characteristics of the opioid risk environment. This includes social, economic, policy factors, that sort of thing. So that workshop can be accessed and watched in total, and also the slides can be shared. Susan will probably share some of that in the chat if she hasn't already. So today I'll be going through geocoding and integrating community data. And then next month, Dr. Lin is going to talk about developing spatial access metrics. So how can we'll be talking about enabling resource community data today, but then how can we start to develop more sophisticated metrics to measure access to, for example, medication for opioid use disorder, and then bring that into analytics or visualization in multiple different ways. So that's next up next month. We should still have a few spots available. And this workshop is also accredited by for CME credits. So for physician credits, the UChicago Principal School of Medicine it provides continuing medical education for physicians. This activity that you're part of right now is eligible for a max of 1.5 credits. So if you're interested in this, or if you're in a field of another health professional field that is interested in receiving this credit, there was some information already attached in an email that I sent to all of you yesterday morning. So that will guide you step by step for how to access that credit. If you have any questions about getting your credits, Tom Weber from the Center for Continuing Medical Education is your contact. So his information is here. So what are the learning goals of today? Well, we are going to learn applications of opioid risk environments in R with resource and community data. Again, for some of you, so we'll be using in later extensions of the workshop, we will use data that was pulled from the census. But for those of you who are interested, I'll also leave you with some tools for pulling your own data from the census using R, using their API directly. We're also, of course, going to understand or review the basics of spatial data analysis. Many seem to underestimate the complexity and nuance of what spatial data analysis is or is not, for that matter. This is a field that has been around for over 100 years, and then in the past 2-3 decades has really grown in complexity with the kind of advancement of computer science, and analytics associated from that. So we're going to just kind of scrape the beginning of the surface of some of this, but hopefully we'll whet your appetite for more. We will also geocode and map resource data. So you're going to have address level data that you will then turn into points on a map. And then finally, we will link and overlay resource data and community data in a series of maps. So you'll note throughout this workshop that the final products are going to be maps in many cases, but the majority of our time is not talking about maps, it's talking about the data and the data processing. And that's a very common feature of what spatial data analysis and geographic information science is all about. So for this workshop, before we kick off things officially, I ask you all to fill out our pre-workshop survey that can be accessed here. So bit.ly/OEEPS/pre. And then for the interactive portion of today, you'll need to have a working R and RStudio environment with key packages loaded. I already emailed you what those key packages were, but we'll review them again later. And you'll also hopefully have your toolkit opened. So the toolkit that we're working from is another resource that our group generated last year. This toolkit provides an introduction to GIS and spatial analysis for opioid environment applications to support communities with better data analytics and visualization. It's really geared towards those who have, again, a very basic preliminary understanding of R. You may use R every day, furthermore, but for your own research. But if you've never used it with spatial data, there's still going to be a lot of new things. So if you're brand new to R and have just been getting familiar with it in the past week, or you're very familiar with R, but maybe not spatial data, there's still a lot of there's kind of an even playing field from that perspective when you switch over to the types of data structures that we're going to be working with. And then finally, there's a zip folder, check your email, that will contain data files. But FYI, let's see if I can move this stuff down here. So this is the toolkit that, this is the GitHub repository rather for the toolkit. You can see some information. We're going to be working with the first few chapters today, but there are more chapters that will be written. If you'd like, you're always welcome to grab all the information, all the data, all the files, all the R Markdown files. You could just, this big green button right here that says code, if you click on that, you could download the entire zip file and work with that if you'd like. Totally possible, doable, really up to you. We're going to work with the data in a slightly different way today, but I just wanted to make sure that all of you knew that that was an option. So another way to access this toolkit, which will be something that that might be a little bit more useful, and this is how we're going to be using it, is here. So this is essentially a book down document, this toolkit right here, and it's going to tell you what are the following libraries that we're going to be working with the most often. So you can already start to download that. It gives you a little bit of the information about the backgrounds of this. We're going to be covering aspects of chapters 1 through 4, but then giving you little tidbits of chapters 5 and 6 towards it. We'll be talking about thematic mapping aspects throughout. And then for the census data wrangling, for those of you who are interested, that will be made available as well. So again, just feel free to navigate to that if you haven't already. I'm sure the link has been posted in the chat. If not, it will be shortly. All right, so let's talk about a little bit more about what our spatial program does at the MARC. So our goals, our spatial program goals, again, this is part of the wider JCOIN network initiative. The spatial program at the MARC, our goals are to, 1, abstract the risk environment for OUD or opioid use disorder populations. We do that in a variety of ways. So our group works on refining access measures to evidence-based medication for opioid use disorder. Obviously, though, access to evidence-based medication is not enough. Health is a multidimensional facet. So we also incorporate different social determinants of health, policy, and other justice setting measures. Anything that we do, we share as data, methods, toolkits, and also sometimes it's not in a toolkit form. When we wrangle data, we'll also provide code for how we wrangle that data so that it can be fully transparent and then replicable for other researchers. And then we also will be developing interactive mapping resources in the last 2 years of our program. So that's our big first objective. Our second objective is to do exploratory spatial data analysis of the OUD risk environment. Here, we love the term exploratory because it means we're coming in with an open mind, meaning we're not just trying to confirm something that we already expect, but we're also trying to uncover unknowns. And exploratory spatial data analysis has a long tradition going back to the 60s and 70s. At the turn of computational statistical revolutions to really, again, uncover unknowns in addition to looking for trends and relationships that we might expect. And then finally, we also are interested in not just exploratory, but the confirmatory extension. So how can we actually evaluate the impact of medications for OUD on OUD outcomes over time? Again, in this case, not just, in order to do this in a successful way, we also have to account for these other more complex community contextual factors and other changing policies over time. So in order to get the data for that more robust counterfactual quasi-experimental analysis, we really need to first have sound cleaned data. That is what the first few years of this project has been. So across the wider network, our job is to integrate, inform, collaborate. Many of you we've already talked with, collaborated with, and again, hopefully that's just the beginning. So I'm not going to go into detail here, but again, our program really moves from data collection to the exploration of data and trends, and then to more quasi-experimental frameworks. A lot of what we're presenting on in our workshop series this summer is really the end of the data collection phase, right? So at the workshop last month, it was really about going through all the, again, all the risk environment data and contextual information at multiple spatial scales. So data was recorded at tract, zip, county, state levels when available. But then today we're going to shift into the methods for not only how did we, wrangle some of that data, but then also how can these tools for geoprocessing, analysis, and visualization be made accessible to the wider JCOIN community so that the community can also think of new ways to consider the data, extend the data in ways that our group hasn't, right? So it's part of that open science tradition. So now let's talk a little bit about what spatial analysis is. This is the condensed version, right? So I could talk about this for 10 weeks as I do in our intro courses, but in 10 slides or less, what is spatial analysis? So we're going to just talk about mainly what spatial data is, because spatial data is at the heart of spatial data analysis. Spatial data is essentially data with both information, so your attribute data that you're familiar with, working with in CSVs or Excel files, that sort of thing. But it also has a location attached to it. So spatial data is data that contains information about specific locations. The information is going to change depending on where the location is. If there are, it will do that. On some occasions, spatial data may only include the location. So you might just have a ID of a point or ID of a specific area, and that's it. But on the converse, without location, the data is no longer spatial. So spatial data is always regular information plus more, okay? There's many different types of spatial data. There's primarily two ways of working with this. Either we work with vector data models or we work with raster data models. Vector data models is what many of you are familiar with when you're using Google Maps, right? So you see point locations that have specific business names attached to it. You'll see roads that correspond to streets, right? So those are lines that are representing roads. And you'll see areas or polygons, right? You'll see the outline of a block. So this is a vector data model that's used, that you're probably already familiar with in Google Maps. Well, some of you might also like turning that layer off and turning on a satellite layer in Google Maps. That's going to be what we call a raster data model, where instead of point lines and polygons, the entire surface is pixelated. And depending on the resolution of the pixels, we can get different types of information. So again, two different ways of dealing with data in spatial formats. Our group really will focus more on vector data models for the type of analysis that we do. And that's really common for kind of social science and social science adjacent research. Today, we're going to work with data set you're very familiar with, CSVs. These are comma separated values or other types of text files. This will store quote unquote spatial data as potentially a longitude and latitude column, and the longitude and latitude column will represent coordinate locations. So last month we talked about CSV data, how it can store spatial data, but today I'm going to update that a little bit and suggest that what you see here could be spatial data, but it is not yet spatial data. The longitude and latitude fields on their own don't make it spatial data. We have to actually change the data format slightly to convert it to a true spatial data format. We actually have to enable the latitude and longitude. And this is where things get a little bit more complicated. Well, last month you also, for those of you who attended last month, or those of you who are brand new, another very, very common spatial data format is shapefiles. So many of you today may work with shapefiles in ArcGIS or QGIS, but you're here because you're interested in learning how to do that in R. Others of you have never heard of a shapefile. A shapefile is a proprietary data format by Esri, which is the same company that makes ArcGIS, which is the major proprietary GIS software out there. There's at least 4 extension files, a .shp, .shx, PRJ, DBF. The DBF data includes the attribute information. It's basically a database file. The PRJ extension will hold the spatial projection information, which is what we'll talk about in just a minute. And honestly, I never remember what the SHX file does. But the SHP file kind of, when you are adding a shape file, you add that .shp file. That's the like master file that stitches the other pieces together. It's very important that you always have these 4 file extensions together. If you have the DBF file in a different folder, it will not be recognized as a shapefile. So this is a really important part to think about. Another type of format that we'll work with that is increasingly more common is a GeoJSON file. So if you're getting your data from a data portal or from a web mapping tool somewhere, it might not be in a shapefile. It might be just one file and it might be called a GeoJSON. So that's an open standard format for encoding a variety of geographic data structures. Something to know is that while in the non-spatial world, a lot of folks just deal with CSVs, in the spatial world, there are dozens of different spatial data formats. Okay, so there's GeoTIFFs, there's GeoPackages, there's GeoJSONs, shapefiles. We're really going to focus on 2, shapefile, GeoJSON. But I just wanted to show you that, again, it can be more complicated. Different groups might have different preferences. If you work with a GIS team where everyone uses ArcGIS, they're probably going to want to talk about shapefiles because that's just so endemic to that way of learning GIS. In contrast, if you're working with a bunch of web developers who might have been learning JavaScript and then just shifted over to spatial recently, they might not even know what a shapefile is. They might primarily work with GeoJSON files. So it's just good to know that these are the 2 major formats that you might encounter. And don't be alarmed though, all the different tools we'll talk about today will be able to read each of these formats. So it doesn't really matter how it's encoded to start with, it just matters that we know how to read it in. So you should at the very least just know what the spatial data format is. So R, okay, so in R, we are going to work with a lot of different spatial libraries, but the key library that is the paradigm of the spatial our work that we're going to be doing today is something called the SF library. SF stands for simple features. But that being said, so when we're using SF, it's going to be using different data structures. Well, why am I talking about data structures? Before, we were talking about data formats, right? So CSV is a non-spatial data format that might have spatial information that we can turn into a spatial format. A shapefile, a GeoJSON, these are probably new to you formats that have spatial data. Well, when you're working with R, you're going to read in a spatial or non-spatial data format, but then in R is going to understand that spatial format is a different type of data structure. So R has its own way of thinking about data. So the really common way, the classic way that R thinks about data is a data frame. And a data frame is simply a table or a two-dimensional array-like structures. So there will be rows and there will be columns, okay? For those of you, feel free to raise your hand. How many of you have worked with the tidyverse? Anybody? Okay, so there's a couple folks. So the tidyverse, so there's at least 3, maybe more folks. So the tidyverse is kind of a modern quote, and this comes from their language, it's not mine. It's a modern reimagining of the data frame structure. So in R, there's the base R structure. So that means you're working in base R, you don't have any other libraries loaded, and this is essentially the basics of R. Well, through Hadley Wickham and a whole shifting data coding philosophy, there is now what's called the tidyverse, which is a different way of thinking about working with data. And a data structure that comes from that is called the tibble. So I'm just going to drop that there and say it is, from their perspective, a modern reimagining of the data frame. Some of the data that we'll work with will have both a data frame structure and a tibble structure and something called an SF structure. The SF structure is essentially what the spatial format is. So SF stands for simple features. It refers to an international standard that describes how objects in the real world can be represented on computers. And the focus is the spatial geometry of that object. So we can have many different types of simple features, points, lines, polygons, and then something that sounds kind of complicated, multi-points, multi-polygons. So when you're just starting with this R spatial ecosystem, you don't necessarily have to worry about the nuance and the detail here, but just having some familiarity with what these phrases are will be helpful in troubleshooting, just to kind of understand, you know, what data structure am I working with? So if you, for example, this happens where folks will try to map a data frame and it just maps a scatter plot. Well, it's mapping a scatter plot because it's not recognized as a spatial object. So it has to be a spatial object in order to be mapped, right? Alex, I think you had your hand raised.
Sorry, that was about working with the tidyverse.
Oh, say that again.
I said that was about working with the tidyverse.
Got it. So yeah, and so so the tidyverse, again, this could easily be its own workshop. For our purposes, we won't work, we work, so tidyverse is increasingly becoming best practices for different types of social science research. Some people have really strong opinions for that, so take that as you will, but a lot of the things that we'll be working on today may have tidyverse happening in the black background, but don't be concerned if, like, we're not going to get into anything that's really thorny on that end. Okay. And then again, what is the R spatial ecosystem? There is a huge R spatial community out there. It's a growing community. It's super active, online, social. If you don't have a Twitter account, get one because Twitter is increasingly the best way to ask questions about R spatial things and get them resolved. So they even have, I think, weekly like R spatial chats where you can ask your R spatial questions. It's a massive community. A lot of investment from our studio is going into supporting this community as well. There's a massive R medicine community that's getting more interested in spatial stuff on the R side. For those of you who will be attending the R Medicine conference next month, at the end of the month, I'll be doing a workshop on this same kind of thing. So huge community. We're working with the SF framework, as I mentioned. That's that purple line that you see right here. So over time, different packages get different types of usage. SP used to be the traditional way of working with spatial data for quite some time. It's recently been switched over to SF. That's a whole long conversation. Happy to talk about that in the QA later, but we're working with SF because it's increasingly become the dominant library. You can just see that explosion in just 1 year, 2020, how it's, you know, the downloads have really massively exponentially changed, right? So that's why we're working with SF. You'll also see, so like a lot of folks love ggplot and ggmap. That's not as common for mapping anymore. Increasingly SF and tmap and sometimes leaflet will be a little bit more common, but there are some really nice extensions in ggmap if you are interested. So here are some resources. If you want to really deep dive, this geocomputation text is stellar. If you want more kind of piece by piece tutorials just to kind of get your feet wet, here are 2 more options. The last one is an option that is developed through a different, or the Center for Spatial Data Science. And this middle one, the R Spatial, that will have slightly more of an SP flavor to it. Okay. All right. So before we dive in and I'll have another few minutes for Q&A in just a minute, but a really big part, like the pink elephant in the room of working with spatial analysis in R, is spatial reference systems, right? All of the data that we work with in spatial analysis has some connection to some place on the Earth. And it turns out that telling or communicating to a computer where that place is not straightforward. So we need a coordinate reference system, or CRS, to communicate what method should be used to flatten or project the Earth's surface onto a 2-dimensional map. Different CRS will imply different ways of projections, and you can get completely different maps depending on what CRS you use. You know, many of you, and when you think of what the world looks like, it's probably a traditional Mercator map. I'll show you a picture of this in just a second. Mercator maps do a terrible job for the poles. So it makes Antarctica look like the size of all of North America, which is simply not true. So depending which coordinate reference system you use, there's different implications for visualizations, but as you can imagine, there are also massive implications for how angles can be distorted, how distance can be distorted, how areas can be distorted. So practically, when you're working with SF, 2 functions to kind of bookmark. One will be st_CRS. That's going to give you an opportunity to check what CRS you're using, but then also st_transform, and that will reproject the data into a different CRS. And don't worry, we're going to go over this in just a minute live, but I'm just giving you some background. So again, so here we're looking at 3 different types of maps or map projections. Our Mercator projection, which is a conformal. And I'm not going to get into the details of what all that language means, but just to kind of give you an idea, Mercator is what many of you are familiar with when you think of the Earth. Lambert conic is another type of projection. This is equal area, where it's really focusing on preserving area. So areas are equal throughout. And then a compromise map does a little bit of both. So it's wrong in both directions, but it just, you know, feels a little bit nicer. So you may have also been familiar with the Robinson type map, even though like this Lambert conic map, that's probably one of the most efficient ways for having an equal area accurate representation of, at least in this example, the North Hemisphere. As you can see, depending which map you use, you can get different types of distortion for both area and angle. For the Mercator map, the further away you get away from the equators, the more extreme your distortion gets, meaning higher error. But you can also get angular distortions. So the angles on a Mercator are pretty solid, but the area is severely compromised, and so on and so forth. And here is my favorite projection. It's a Buckminster map or Dymaxion map projection. This is imagining the world as this kind of polyhedral surface that is as close to a globe as possible, and then essentially unflattening it into something that attempts to preserve, again, area, distance, and some of these other pieces as much as possible. However, that final flattened out map makes it very difficult to use on a daily basis. So again, just really highlighting how important the CRS is and how there's no one perfect CRS. When you're working with spatial data, a spatial reference system is going to be required, and you are already using a spatial reference system if you're working with spatial data, whether or not you realize that. I'm going to throw in some language here that will be important when you're working with R. So spatial reference systems will commonly use what's called an SRID integer, spatial reference integer. And the most important acronym here is an EPSG code. So when you're working with R, different spatial reference systems will be represented with different EPSG codes. EPSG stands for the European Petroleum Survey Group. Now they've renamed themselves International Association of Oil and Gas Producers. They had one of the most comprehensive databases that store thousands of different projections, right? So if you're in geology, having precision is really important. So a lot of these spatial techniques will come from that tradition. But EPSG, when you are trying to find a reference system that matches what you need, EPSG is the magical acronym that is going to get you that information. So again, I know that's a lot, but just work with me here. The most commonly used EPSG today is EPSG 4326. So if you learn nothing else on reference systems today, remember EPSG 4326. This is the most common projection. It's used in Google Maps. It's used in, if you have a phone, your phone is using EPSG to report and visualize spatial data. If you have a GPS unit that's like for civilian use, it's very likely using EPSG 4326. This is a conformal projection system. So kind of going back here, you can see the pros and cons of conformal systems. Notice that there's the least angular distortion, but aerial distortion, maybe not, right? But again, it looks pretty, so that's why a lot of services like Google Maps use it. Something that's really important to consider, though, is that distance in this code, in this reference system, is not measured as feet or miles. If you have an XY location that looks like this, and it's an EPSG 4326, if you calculate the distance from 2 points, you're not going to get a real measure in feet or miles. You're going to get something in degrees, okay? This is a really common error that a lot of people make. And as you can imagine, where you are on the Earth, the degrees change, right? So if you are calculating the distance between two areas across the United States, EPSG 4326 will give you an output, but it will be a problematic output. That doesn't mean anything other than degrees. So that's important to know. That being said, when we're working with geocoded data, we're going to get a latitude-longitude coordinate. That latitude-longitude coordinate is very likely EPSG 4326. So we have to use that projection first to transform the data table into a spatial format. Later, we can transform it into a different projection, but this is one of the most challenging gotchas for folks just learning spatial analysis. Okay, so beyond that, we're also going to learn today about some very, very basics of thematic mapping. There's different types of thematic maps or choropleth maps. We can have maps with quantiles, which are really common in public health, equal interval, which is almost, similar in concept. That's going to be more of a traditional, if you think of a histogram and how data is measured in histograms, is a default that is usually that approach. But then also more complex maps like natural breaks, which is essentially performing a clustering algorithm on one dimension of data to find the optimal break. So some of this is repeated from last month, but just those terms of choropleth map is really important to be familiar with what we're trying to generate here. But we're also going to be doing something called generating a map overlay. So you might look at this and just say, oh, that's a map. Well, it is a map, but this is also a map, right? So this map shows a choropleth map. Here we have a choropleth map and then an overlay of additional data. So what you're looking at here right now are 3 different data sets. We have COVID case data by zip code in Chicago. That's one data layer. Another data layer are those points, which are individual resource locations that represent methadone providers. But then we have a third data layer that we're going to generate today that is a buffer layer, or essentially a buffer of about 1 mile around each of those methadone resource locations. Okay, so those are 3 different layers and we are overlaying them on top of each other. I could also add a base map, which would be just a reference map that is, you know, what Google Maps looks like or something like that. If we add that, that is now a 4th data layer. So to generate maps that look like this, we have to think about each data layer separately. And in some cases, generate new layers to kind of filter in here. So before I go on, any questions at this point that are more from a very broad macro perspective? All right. Okay, well, you guys are still here, which is super. So first things first, we're going to want to set up our spatial, our environment. So at this point, I'm going to make my window a little bit smaller. Okay, and let's see here. I'm going to switch over to my toolkit. So my toolkit is right here. Okay, I can see that on the left-hand side. On the right-hand side, I'm going to add an R window. Here, I can even make this a little bit smaller if needed. Okay, so here I have my RStudio loaded, right? This is my RStudio. I have downloaded, just so that you can believe me, I have downloaded the workshop data onto my desktop. So you want to make sure that your folder with all the data that you've loaded or unpackaged for this is really clearly available to you. Okay, that's a pretty important part of setting up your working environment. So here I have my environment in RStudio. Maybe I'll just make it a little bit bigger for a second. A tip for setting your working directory, which is going to be a really important thing, is going to be so. Let's see here. Actually, let me go back here first. First things first, we want to make sure that you have set up R and RStudio. And then here we're going to install the following libraries: SF, TMAP, Tidy Geocoder, Units. Units isn't really required, so we can convert units with algebra, but if this is kind of a nice additional piece if you need. So I included gotcha for SF. So several Mac users have difficulty installing SF. I link to just Google SF GitHub at the GitHub site for SF. The simple features our library. There are additional tips for Mac users if you need it. So again, don't be alarmed by that. It's something that happens to a lot of folks. Also, just restarting and that sort of thing can also be helpful. So you need to have SF and TMAP for this workshop. We're going to also be working with Tidy Geocoder. So next, you need to set up a data management system. That's what I was just starting to talk about. I unpackaged my data onto my desktop just to make it easily accessible for this. And then you want to set your working directory. So with my working directory, if you go to Files in RStudio, a really nice kind of shortcut is going to your desktop. You can see my lovely junk folder called Stuff, right? You can have junk drawers, but also junk folders. And then here we have this spatial workshop available to us. So all the data is unpackaged here. If I want to set the working directory, I can click on More and Set as Working Directory. And at this point, I may also want to create a new file. So earlier I showed you if you want to grab everything from the toolkit, you could work directly from the R markdowns. For those of you who are familiar with how to do that, I'll just leave that to you. But the rest of this, I'm going to essentially create a script to work from that I'm basically generating on my own, looking at the toolkit information and kind of going from there. And that's really useful so that if there are errors, I can kind of understand what was happening, what steps are needed, and that sort of thing. So here I'm going to create this new R script. I'm going to call it workshop 2. I can call it a scratch. So this is just like my working R script. Everyone has their own styles for this, and that's totally fine. So I'm going to save that. Then I'm going to set my working directory here so that I know where I'm working with. Okay, so we've got that. Let us go back to our toolkit. So let's see what we have to do first. So I'm going to go to the geocoding resource location chapter in the toolkit. And here, it kind of starts off with just a little bit of an understanding of why we're doing what we're doing. So a common goal in opioid environment research, especially when you're thinking about risk environments, is to calculate and compare access metrics to different providers of MOUDs, right? So before we can run analytics for that, we need to first figure out what to do with the data that we have. So in the data that we have, if I look at my desktop folder, I have this CSV file here called Chicago Methadone Node Geometry. If I were to just open that up in Excel, which is a starting point for many folks, right? Especially if you're just making the transition, we're going to get this information. And this is something you could download directly from SAMHSA, right? We have the name of something, we have the address, the city, the state, and the zip code, all right? In order to do geocoding, this is really the minimum of what you need. You need an address, city, state, zip code. If you don't have that, your error for geocoding is going to be very large. So first, kind of keep that in mind. Note that some of the names that we have here, we have an empty name. That doesn't matter though, because we have an address that we can convert into a location, right? So before you do geocoding, I always recommend looking at the data that you have and whatever system that you prefer, right? You can open it up in Excel, you can open it up in Geoda, which is something we went through last quarter or last month. However, or you can look at it in R, right? However you'd like to look at it, inspect the data and just figure out how messy is your geocoding data. And here, note, we're focusing on resources because the geocoding service I'm going to go through today pings, it requires the internet to search for each address. That means that it's not HIPAA protected, right? So having HIPAA protected data get geocoded is going to require a little bit of more finesse because you essentially have to have a geocoding site offloaded onto a server that you're then pinging. I'll give some resources towards the end for those of you who are interested in that. But again, we're going to just focus on resource data because that can also be really useful for what we need to do. Okay, so we have that information. And again, geocoding, we're turning the address into geographic coordinate reference systems. In this case, all I had in that geometry file was the information that you saw. There was no metadata file attached to it. It doesn't tell me what reference system was used, what coordinate reference system was used. So I have to make a call. I have to, I'll have to decide. Okay, well, and we'll talk about that in a second, but we're going to essentially geocode the addresses into geographic coordinates. If there was a geographic coordinate there already, like a latitude and longitude, then I'd have to decide which projection to use for that next step. Okay, but in this case, we start with this input data. I provide you with one already, and you can also find that available here if you'd like. But the next step is essentially we are going to have to download some libraries. So here we have, all right, I'm going to download the SF library, and I've already installed it. Note, if I had not installed it, I would have to do something like this. right? But in this case, I've already installed it, so we're good to go. So I'm going to first install that, and it's already been loaded. I'm going to next want to do the tidy geocoder. Okay, and then I'm going to install TMAP. So SF is going to do a lot of the geoprocessing work for us. Tidy geocoder is going to geocode our information, and then TMAP is going to map our data, which is going to be pretty fun. All right, so next up, we're going to load our data set. If I were to just copy and paste what I see in the toolkit here, and let's see if I would get an error. Yes, I would get an error. It says cannot open data/this. Well, that's because I don't have a data folder in this directory. So in this case, I am just going to delete the data part right there. And here I can see that I have the exact same CSV name here, right? And I've already inspected it to be sure that that has the address information that I want. So we're going to run that line. Okay. And now let's look at the data, right? This is something that is going to be pretty important when you're working with spatial data. And it's also just good practice in general for this type of work. Let's look at the data that we have just loaded. So here I can see the unique ID, the name, the address, the city, the state, the zip. Okay. So again, at this stage, the toolkit recommends doing some quality control. I've already talked a little bit about that. So we can kind of plan to go to the next step. So just from first view, this data set looks like it's pretty doable. Or like there's enough data that we can use to generate, we can convert a full address from the information that we have there. Each geocoding service that you use is going to have a different requirement for what the input is. We're going to be using Tidy Geocoder. If you look up the documentation, essentially you need one input that is going to be the full address. The full address will be the name and street, the city, the state, the zip. We have to essentially put all of that into one line of code. And the other, so that's one thing to consider when you're geocoding work. Another aspect is going to be, well, which geocoding service will you use, right? This can be a massive topic on its own. Esri, ArcGIS, they have geocoding services available. Google Maps API, they have a geocoding service available. We're going to be using what Tidy Geocoder includes, and that will use the census geocoder as a default. And then if it cannot find the address, it will then try the OpenStreetMap geocoder. So these are the two methods that are available with Tidy Geocoder. You can essentially either tell it to use one or the other, or you can select the option Cascade, which it will query multiple geocoding services until it gets an answer. Okay, so starting with the census and then going from there. Each geocoding service that exists has different, again, input specifications, but also different types of services available. So the US Census geocoder allows about 10,000 addresses to be coded at one time. So you're pinging the API at the census 10,000 addresses at a time. Google Maps, they also have a limit, but it'll be a daily limit. You can only geocode so many per day. And then Google Maps and Esri also have paid for versions. So for example, the Esri geocoding service is very excellent, but it costs a lot of money to use that. And it just, again, depends on the credits that your program has and that sort of thing. So there's a really complex financial scheme to all of that. We're kind of sidestepping all of that by just using an open source free geocoding service with a pretty reliable option, either the census or the OpenStreetMap. That doesn't mean that it's perfect. So whenever you geocode data, you should still plot it and inspect it just to make sure that it's doing what you think it needs to be doing. So first, before you just throw all of this data at the geocoding service, it's best practice to look at a sample. So here we're going to geocode a sample, and this function here, geo, is what the Tidy Geocoder is doing to geocode something. So we're going to pass a full address that looks like that. We're going to say, give us a latitude in this format, the longitude in this format, And then the method will be that cascade method. So I'm going to run that. Okay, it takes just a second. And now if I inspect my sample, I can see that I get a tibble, right? Remember, that's one of the data formats I warned you we could get. It's a fancy, data frame. We have the address as a character, we have the latitude, we have the longitude, and we have the geographic method used for geocoding. So it used the census data set. All right, so here that worked. So I think we're ready to go. Next up, we're going to look at the structure of our methadone clinic. And that's because it's going to be very helpful just to make sure that the data is the format that we expect it. So the data structure is a data frame. And here we can see that the address is a factor, the city is a factor, the state is a factor, the zip is an integer. Okay, factors can be really annoying and are, if you're new to factors, that will be for another day. We're going to just give you a tip here. So this code right here is going to convert the address, city, state, and zip into a character format. And it's going to paste it all together so that it's all in one line. This is going to give us a complete address. Now, if I look at our methadone clinic site again, we can see we have this new field added called full address, and that's going to be the entire thing, the whole thing. So at this point, we're ready to geocode. Okay, I'm going to just grab this part here. So this is the geocoding function. It is taking the methadone clinic's data set and it's geocoding it so that we have the full address as an input, latitude, longitude, method cascade. Okay, I'm going to just run that, and this might take a couple of seconds. And again, hopefully you guys are also trying this in real time. Any questions while we're waiting for the geocoding service to return? What do you guys think? All right, either I'm doing a terrible job and no one has questions because they're confused, or I'm doing a wonderful job and all of you are totally understanding what's happening. It could really go one way or the other. Okay, and so normally when this is geocoded, you're not going to be running a Zoom session that is taking up some juice on your system. So normally geocoding doesn't take that long, but again, I'm just impatient. So that seemed to have worked. And if I look at the data here, here I can even probably look at the geocoded clinics. And if I look at that, I should have two new lines, latitude and longitude. So it seems like everything was geocoded except for these two lines, right? So this is a problem. We cannot take latitude, longitude data that is null and convert it into a point, because how do you turn something, or how do you turn nothing into something? At this point, we have to make a decision. So in the text here, it gives you some different options. We can either decide to investigate the specific address and add a new address and kind of exchange that, or we can do something else, right? So oftentimes when we have addresses that don't totally geocode correctly, again, we have to make a decision. Oftentimes the decision will be to scratch it. So for example, if you're a lot of times humans are inputting the address and you have to decide how, either you're going to validate that specific address or you're going to toss it out. Any ideas for how we could toss out these two rows in order to kind of continue? That's where the interactive part comes in. Any ideas? Yes, no, any ideas at all? Hey, I teach undergrads. I can sit here all day. Any ideas at all?
Alex just shared in the chat just to remove the rows.
Yeah, I mean, let's remove the rows. So, I mean, we could use an old classic na.omit. You know, this is kind of we have to be careful with this because na.omit may also remove anything with any null data, but you know, in this case, just to kind of get things moving along, that might be okay. Okay, so this is, again, this is the big hammer. Anything that is null, we're going to remove here. We lost 2 observations. We can look at that observation here. So we no longer have those first 2 addresses, okay? But again, just be really, really cautious when you do this. You'll find that with spatial analysis, there are dozens of assumptions that happen, or assumptions and choices that are made throughout, and that can really impact the final data set that you generate. Okay, so next we have to turn this geocoded data into points, right? We still just have a glorified data frame, or Tibble, excuse me, at this point. We have to turn this into spatial data. I mentioned before that 4326 is going to be the favorite reference system of many different things online. Well, it turns out the geocoding service that we used also used 4326 in order to geocode that. How would you know that? You'd have to really dig into the documentation of that. And, you know, I'm just telling you that's what the geocoding service that used provided. So that is going to be that. So in order to turn this into the wonderful spatial point data set that we want. And first, actually, before I do that, let's see what happens if I plot this data. Right, if I plot this, right, it's saying we don't know what's happening, this doesn't make any sense, et cetera, et cetera. So again, we'll see in a minute, if we switch this to spatial data, it's actually going to suddenly be able to plot in a pretty cool way. So the wonderful function that does this, it's just one line of code. We are going to do st underscore as sf. We're going to use our geocoded clinics. We're going to assign the latitude and the longitude. Note we say latitude, longitude, but it's actually they're reversed. So longitude is our x coordinate and latitude is the y coordinate. So this is just something with our language. It's easy to switch. And I have seen data portals out there that make that mistake as well. So this is another step where it's really easy to make a mistake. If you use the wrong coordinate reference system, or if you flip the coordinates, you could get something that's plotting on the other side of the world. So if you have an error after you enabled your data, it could be because, again, either the coordinate reference system that the geocoder used was incorrect, or the coordinate reference, the coordinates were reversed. And here, also note, this function works for anything that has a latitude and longitude. If my data set looks like this and I have a latitude and longitude, I can turn it into a spatial data set at this step, okay? So at this point, I'm going to plot. And here I can see I'm no longer getting an error. This is actually plotting some points in space, which is, again, pretty cool. Another cool thing is if I look at the data, I'm going to see something a little bit different. Okay, I'm going to see the same attribute information from before, X, name, address, city, state, but now I have a new, something new. It's a simple feature collection, a geometry type point, okay? So I have the same attribute information as before, but now I've added new spatial dimensions to the data. And at this point, we can do some pretty cool things. We're going to switch to TMAP and use the view mode. So the view mode is going to give us an interactive map view. And at this point, we are ready to map some data. So the way that TMAP works is first you add the shape. So what is the first shape that we want to add? Well, in this case, we just have one shape. We have the point data that we want to add. This is a point data set. So I'm going to use a function called dots because that is what we have. So if I click on that, it is giving me this really nice map that is interactive. And I can zoom in, I can click on one of these, and it just gives me the ID. I could also switch to a different base map just by clicking that. If I want to get really wild, I could also zoom in, right? So that's another option. And then I can also export as an image, as a clipboard, and that sort of thing. So this is going to be really useful for a lot of different things. So at this point, there's another option here. So you can even add, specify the base map that you want and kind of go on from there. Okay. All right. So this is the geocoding chapter. And this does take a little bit longer, especially because you're kind of just getting familiar with what the things are happening here. Okay. All right, next step is the buffer analysis. So now we have these gorgeous points. I want to create a buffer around it. So why would I want to create a buffer around it? This might be saying I'm going to generate a service area around each provider that is walkable. So that might be, let's say, a 1 mile walkable area around each point. Okay, so that is going to be this next chapter. In order to do this part, I'm going to want to bring in some new data. So here we can bring in zip code data, city boundary data. Here, I don't have to bring in the methadone clinics because I've already created the spatial spatial object in my R environment. If I wanted to save this as a shapefile or as a GeoJSON, I could also do that. That's at the end of the geocoding resource tutorial. But at this point, let's say that I wanted to bring in zip code data, but I didn't know where to get it. And this is something that commonly happens, right? You want to bring in some data, but you don't know where to get it. Well, I want to bring in zip code data from the city of Chicago, right? So how could I get that data? I might go to the city data portal, and here I could just write maybe zip boundary. You can see if that works. And it turns out the first thing that shows up is boundaries/zip code. So I'm going to click on that just to inspect to see if this is what I want to bring in. Okay, this looks right. This is zip code data. It definitely looks like something I'd want to bring in. I'm going to click on export. And now I have a lot of different options for how I can download this data. So in this case, I'm probably going to want to download it as a shapefile. You could also download it as a GeoJSON, but let's just say shapefile for now. I'm going to open that file. I'm going to copy this and I'm going to paste it in this folder right here. I'm going to just grab the name of that. And with this information, now I can read in. So here we're going to do buffer analysis. At this point, I can actually read in another data set. So I'm going to use actually, here, I'm going to switch back so that we're not too off sync with what is recommended here. I'll make this a little bit smaller so we can see that. Okay. So at this point, and again, you can pull these in step by step. I also include the boundaries file in your zip file already. And at this point, again, we've already loaded in our clinic, so we don't need that. At this point, I'm going to say that I want my areas information to read as such. So I'm going to have that. And then instead of reading from that file, I'm going to read from this file. Okay, let's see. Well, I can see it exists, so let me try that again. All right, now it loaded correctly. If I want, I can plot the areas just to make sure that I'm getting something that makes sense. And indeed, here I can see some zip codes, so that looks pretty nice. If I wanted to, I could also read in the city boundaries. Okay. And if I plot that, you can see what that looks like. Okay, so there we go. And then up here, another option is, so here I've got, in this tutorial, we now call it not methadone SF, but we call it MET-Clinics. So another option is just to be able to reproduce this code, I might just rename methadone SF as MET-Clinics. Okay, so from here on, we are going to, again, first start with a very simple overlay map. At this point, we've been working in the interactive mapping. Now we're going to move to the plotting, the static mapping mode, so you guys can see what the difference looks like. And at this point, I'm going to just copy and paste the code here that's available. Okay, so what is happening here? I have the first layer. This is going to be our zip codes. If I didn't know what the borders do, I could also just kind of remove that. So here I've got the zip codes. On top of that, the second overlay is going to be our clinics. So let's see if these two things overlay. They do overlay. The clinics are really teeny tiny. So now I'm going to re-add the kind of styling stuff that I had in there and see if that makes any difference. All right, so we can see this alpha actually made the boundaries slightly more transparent. And then the size function made our dots a little bit larger and we are coloring them red. Okay, so we have the beginnings of our map, which is pretty great. Next step, we're going to have to, so the two things overlap, which is fantastic. That is the first step before we do anything else. Next step, if we want to create a buffer, if we want to have a 1 mile walkable surface area, we're going to have to calculate 1 mile. Well, remember what I said before, that the reference system that we were using, EPSG 4326, it measures things not in feet or miles, but it measures it as something else. So if I were to Google, so go to Google, and actually I recommend Google because of the search algorithms that are in place in the our spatial community is more likely to search this way. So that's a specific recommendation. If I were to type in EPSG 4326, the first option over here, it tells me a whole bunch of information about that. What we're looking for right now is unit. So the unit is a degree. Okay, that's not going to be very useful for us. Common question when you're first learning this stuff, well, I don't know what EPSG to use, right? So at this point, we can type in EPSG, type in the place of wherever you are, and then what kind of unit you would like. So let's say feet. You could also type in kilometers. And look at this. The first thing that shows up is this EPSG code right here, EPSG 3435. And then the unit is also US feet. And this is specifically focused on Eastern Illinois. So it's optimizing for that location. And that's great because that's where our location is. All right. So at this point, we're going to kind of come back into here. I'm going to zoom down here and we are ready to check some things. First is we're going to check our coordinate reference systems. So if we're going to check our coordinate reference systems for both the MET-Clinics as well as the zip codes that we have, right? So if I do this, I get the coordinate reference system is 4326, okay? And for areas, it's also 4326, but look at the details here. How these are encoded are different. And for R to work correctly, they have to be encoded in the exact same way. Furthermore, we don't want to use 4326, we want to use 3435 in order to calculate a buffer. So we're going to create a new coordinate reference system. I'm using STCRS here, using my EPSG code. And then we're going to just copy the code here so that you can see how to transform each object into the new coordinate reference system that you would like. Okay. And at this point, if I were to rerun the coordinate reference system, we can see that I get a very different piece of information for Met clinics and so on and so forth. So now we're in a location-specific coordinate reference system, and we are ready to do buffers, okay? All right, drum roll. Buffers happen with literally one line of code. We're going to use a function called stBuffer. You just pass in the clinic information, and then here, so here we have, unit is equal to feet. So we have to figure out how many feet are in 1 mile. Okay. So that is why 5,280 is included here. If you're using a different coordinate reference system that uses kilometers, obviously that's not going to work. Like, you're going to get a massive buffer. So this is another common gotcha point when you're working with our spatial stuff. Okay, so we're going to do that. And at this point, we're ready just to visualize things. Okay, so I'm going to copy what we have here. Or actually, no, we can even just do it this way. So we've got our first layer here. Let's say I'm going to add, so this is our third layer. Our second layer is going to be buffers, and that's going to be a polygon, right? A buffer is a polygon, it's not a point. So we're going to just, let's see if we were to visualize it the same way, what that would look like. I'm going to add my comment field just to make this a little bit easier for myself. Okay. If I make my plot a little bit bigger, I can see these gorgeous buffers 1 mile around each of those pieces. Okay, so at this point, you can get really fun with styling. And I'm going to shift to the last section, but I'll just show you here very quickly that we have a lot of different options for how you stylize each of these buffers. A lot of this is just, looking at the code that exists, updating one thing, changing an alpha value, changing a size value, trying out different colors. There's a couple different options here. You can also do things like, instead of having the buffers overlap each other, maybe you're interested in just having an outline of whether or not the buffers exist or do not exist. That's called a union of buffers. So you can learn about that there. You can save this as its own spatial layer. You can try out a different buffer. And you can, again, so here in this version, we have even wider buffers that are overlapping, and you can create some really cool looking maps. Okay, so all the components to generating these maps are here. It's just a matter of, once you have this spatial data, and here we calculated a new spatial data set, we calculated a new buffer data set. From there on, it's just a matter of how you overlay it and how you're going to stylize each of these pieces. And fortunately, TMAP has a massive amount of documentation for styling. And that's why we teach with TMAP first. ggplot can be a little bit more customized and specific for mapping. For kind of the exploratory data analysis that we normally start with after creating a variable, this is still going to be highly recommended. Okay, but at this next stage, so now we have buffers, we have our zip code information, but let's say that we want to integrate other types of community data, right? So we get one view of the scene of walkable methadone service sites. Maybe we're interested in how that connects to need, right? So during COVID, we know that there was a lot of concern in the OUD community that potential disruption to services or disruption to travel made it more difficult to access different sites. So here we are going to add Chicago COVID cases by zip code. And this was downloaded at a certain point in time. So it's no longer current, but it's just available from the city's data portal from previous work or from a previous data point in time. So we're going to add COVID case data by zip code. And then we're going to add our buffers on top of that just to start some very basic visual analysis. We're not calculating more sophisticated access metrics, but this is just the stage where we're starting to grow and add data to our projects. So with this, in this chapter, you need to have your clinic data, which we have. you have to have your 1 mile buffer zones, which we have, and we have to have zip codes, which we have, but now we also want to bring in this COVID data set, okay? So I'm going to scroll down here, and at this point, I'm going to just copy this file. So this data set is included in the zip that I provided you. We're adding that. I'm going to take away that data folder, and we're able to read it. So if we wanted to look at what this looks like, we can look at the top 6 rows of our COVID data set. And here we can see a lot of different information: the zip code, the week number, the week start, the week end. As you can see, this ends in September of last year. And there's just a lot of different information here, right? And also we have a lot of other things. So, weekly cases, cumulative cases, and what have you. It's really important that the data that you're working with is in wide format, meaning this is going to basically focus on one zip code at a time, right? Which is going to be something to think about. And this can get into more complex data processing, but we'll just, in this case, assume that what we're starting with has at least one zip code per row, and then we're going to be interested in one of the columns of this data set that we're going to map. So let's say we're interested in the cumulative case rate. That's a really common field that is used in a lot of like COVID analysis to kind of assess cumulative cases over time. So this is going to be the variable that I want to include. So we're going to have to clean the data a little bit. If you wanted to look at the column names, so there's different ways of doing that. I already linked, I think, the head option. Okay. All right, so we're going to just very quickly grab this, subset the data. Put this over here, okay. So we're going to subset the data. So we have zip.code. That's our zip code variable that we want to join on. And then we also have the cumulative case rate. So this is the data that we're going to grab. If I look at what that looks like, I should just have those 2 columns. Again, the zip code and then the cumulative case rate. At this point, we're going to want to identify our join key. So for this data set, I'm going to join using zip.code. For our areas data set, I'm going to want to merge using zip, all in lowercase. So these are our join keys that we're going to connect together. At this point, so in this file, it's using a slightly different zip code data set. So the both fields have the same GeoID key. In our example, because we just pulled our boundary data from the city data portal, it has to look a little bit different. So instead of by, in this case, we don't have the same name in both ones. So first we start with the areas data set that we want to merge our COVID data to. So by X is going to equal zip, right? And then for COVID.sub, we're going to use this variable right here. Okay, and if I want to look at our merged data, I can see that we have our zip code, all of the spatial information, but now we also have this cumulative case rate. Okay, now if you'd like to get even more complex, we also have data like or from our OEPS data warehouse, right? We have multiple different access metrics. So that's provided in your data folder already. That's available as a CSV. You also have another suite of demographic information. So I encourage you, kind of for homework, use this same merge concept to join data from one of those or both of those into your master zip code area. It's the same format, but you're going to instead have to figure out what is the merging column name that you're going to merge by in both cases. And you always merge to your spatial master. You have your zip code spatial master, you're always going to be merging data to that, okay? But at this point, we're ready to visualize some data. It's honestly, that's all she wrote, as they say. So we have our merged data. We're going to visualize. So here is a slightly different function. It's called polygons, but it's the same idea as there's just a lot of different parameters to use when you're visualizing things. So don't be alarmed by that. But we have our merged files. We have our polygons. We're going to visualize cumulative case rates. We're going to use a quantile way of breaking up the data. This is a color palette that we're going to use, and we're going to title this COVID case rate. Next, we're going to layer on top the buffers, which we actually are named Met Clinic buffers, so I need to change that. And on top of that, we're going to add the individual points of those different locations. So let's see what that looks like. I promise it usually doesn't take this long. This is just because we're virtually on here as well. Okay, so let's try that again. So as this is visualized, you can again zoom in, you can export this as a web page, you can export this as an image, and TMAP has so many additional features that are available to you. So this, you're going to be able to add scale bars, you can add an update and refine your legend, you can add a north arrow, you can even add a histogram of data like the case rate data that you might want to highlight the different styles that are included. So as that is thinking, I'm going to switch over here just to highlight some of the other features of this toolkit. So in the thematic mapping section, it's going to go through step by step all the other options for how to visualize data. So here we have, it's called the pretty category. It's going to visualize everything in this kind of very simplistic way. Quantile maps, natural breaks maps, and this is using that kind of clustering technique, standard deviation maps. All of this is done just by changing one parameter in the TMAP option, this style, okay? And then beyond that, you can change color palette aspects. So there's a couple tips there. You can use a library called Color Brewer to add even more, to look at all the different palette options that are available to you. Color Brewer is really optimized to develop aesthetically pleasing data classification or bins for different types of things like this. So you can have diverging palette schemes. There's just a lot of different options. So again, this is just the tip of the iceberg. And then also in that respect, we have census data wrangling. You already have an environment. If you've made it this far, your environment is already set up for pulling in live census data. The only additional thing that you're going to need is grab a specific key. So if you follow this toolkit, there's a whole section about enabling your census key. All you do is fill out the form here. They're going to email you a specific key. You uncomment this line and run it, and your system will have a census API key. It's free. You can use it multiple times and just go from there. So in this tutorial, we load data dynamically for a whole state. And you can be very specific in the type of data that you want to pull. So if there's data that is not in the OEPS database that you'd like to pull, maybe from a different year, a slightly different version of a variable, all that's included here. You can pull census tract data, county level data, state level data very easily. Zip code data is a little bit trickier because zip codes cross boundaries essentially of these other things. So if you're working with census data or zip code data, here it will pull it for the entire country. And I'll just leave it at that. So that can be a little bit more complex. But at this point, again, I guess this was a long workshop, but we do have some time at the end to chat. So are there any questions? Are there parts where you guys were getting stuck at? or areas that you'd like to get more information on, please let us know, add your chats or add your comments in the chat, and then also just feel free to ask us and we're happy to kind of follow up accordingly. Oh, and actually the grand finale is the, I promised that map here. And so we can see here, we have the COVID case rate data in the background, and we can see the buffers and the individual points very clearly. So, so again, this is just, again, the start of doing spatial analysis in R, but just through these 3 chapters, it's really gonna, you're gonna have the basics covered, and we've also covered a lot of the common gotchas that happen throughout. All right, questions. The group was really quiet today, so please give us, you know, some ideas or feedback in one direction or the other. We're happy to help. I will at this point flip over just to the final few things of the work. Okay, I'm just going to go back here. And so again, we've really gone through all of this for the conclusion of this workshop. Please feel free again to get more information at the toolkit site. If you want to bring in more data into your R session, all of that is available through the opioid policy scan site that we have. Please fill out the post-workshop survey. You know, feedback is a gift. We love feedback in either direction. It really helps us improve. Obviously, we didn't, you know, this was a probably too much content from one workshop, or maybe it was just enough. So that's the sort of thing that we'd love to know. And then next month, Dr. Lynn will be again talking about developing spatial access metrics. This is where things get even more complex. So having the basics of visualizing things like we did today is going to be really helpful before you get to that stage. And that's it. So thank you guys. Here are our standard acknowledgement page and the policy scan citation for those of you who need to use that. All right. Any other comments here? Super. Thank you so much. Yes, agreed. I think that this is a long haul. There's definitely a learning curve with R, but then also separately with R Spatial. So just taking the time to go through is really helpful. And at the very beginning of the toolkit, we do include some recommended refresher courses. So data carpentries are for social scientists is fantastic. And actually, Dr. Lynn is also a certified data carpentry teacher. So if there's interest in our intro social, like for social scientists or health research, we're happy to set that up a couple months from now. And we can similarly set that up with credits if needed. Cool. All right, thank you, everybody. All right, we'll talk to you soon. Email us if you have questions.